Students, good afternoon to you. So today is the fourth lecture of Information on Theory and Coding series of lectures. And in the previous lectures, we have discussed the entropy, which is average information content of a source, and we have discussed information rate. And we also have taken some of the examples related to average information and information rate. So we people all aware that we represent the entropy for the average information by logarithmic way. Sometimes we represent by log base 2, and it will have the unit of bits per symbol. Sometimes we use the logarithmic of base 10, that will have the unit decits, or sometimes it is called as Hartley. And whenever we are using the logarithmic of base e, or that is called the ln, then we'll get the value of entropy as a unit of nats. So three different logarithmic ways are there. We can use any of the way. So any way you prefer, all are the correct way of representing the entropy. So today what we are going to do, we are trying to establish a relationship in between the bits per symbol and decits per symbol and nats per symbol. So what we are going to do, we are establishing a relationship in between bits per symbol and decits per symbol and nats per symbol. So this unit decits per symbol can also be called as Hartley. Hartley. Hartleys. This is the other name of decits per symbol. So whenever we represent the information as the unit of bits per symbol, so for that the expression is I is equal to log base 2 1 divided by probability. And whenever we express as a unit of decits per symbol or Hartley, then the information is log base 10 1 by probability, so on. If you try to use this unit of as a information, then it will be log base e 1 divided by probability. So it is bits per symbol. This is Hartley, and this is unit is nats per symbol. In this particular lecture, we are going to establish a relationship in between bits per symbol, Hartleys, and nats per symbol. So let me take one of the expression among these three. Suppose I am writing I is equal to log base 10 1 divided by probability, hence the unit is Hartley. Or for your understanding, I can write like this also, log base 10 1 divided by p. This much Hartleys is equal to I. So in this equation, what we observe, this much Hartley is I. So what about one Hartley? One Hartley can be written as I divided by log base 10 1 divided by p. I have taken this particular term to right hand side, so it will be divided. Okay, all right. Hope you followed me. Now what I'm going to do, that in the numerator I have I. So since first what I want to establish the relationship in between Hartley and Nats per symbol. Okay, so the value of I can write this equation. The value of I can write this, or I can write this. So if we want to establish a relationship between Hartley and Nats per symbol, so in the numerator, let us write this value of I. This is log base E 1 divided by probability, and the denominator we will write the same thing which we have written in the previous equation. So this you can see 1 divided by P, it is nothing but P inverse, and this is also nothing but P inverse. So log base E P inverse divided by log of base 10 P inverse. So this inverse, I can take the negative sign to this side, so which is minus log base E of P. In the denominator, it will be minus log base 10 of P. So this minus and this minus from the numerator and denominator, you can cancel. Okay. Now let us follow one logarithmic identity. So logarithmic identity is log base A of B is equal to 1 divided by log base B of A. So this is one logarithmic identity which we are going to follow in this particular equation. Then what I can write, the numerator, that is 1 divided by log base P into E, and the denominator I can write 1 divided by log base P of 10. So what we are calculating? We are calculating here 1 Hartleys. So 1 divided by something, whole divided by 1 divided by something, which I can write log base P of 10 divided by log base P of P. So if any logarithmic terms are divided like this and they are having equal base, so this we can write as log base E of 10. So log base E of 10 is nothing but your ln of 10. So we know we can calculate by using the calculator what is the value of ln 10. So ln 10 is the value is 2.3. And what is the units? Units will be nats. So I think I did one mistake which nobody has identified. I have written here 3 different equations of information. Okay, with logarithmic of base 2, base 10, and base c. So nobody has identified my mistake. So information is having unit of bits. It is not bits per symbol. Rather, when we are calculating entropy, that has the unit bits per symbol. Okay, so please correct my mistake. Okay, so one Hartley we have written like this. So when we replace this I in terms of log E 1 by P, that means we replace this here. So the unit should be nats. So here the unit will be nats. So here the unit will be nats. Here the unit will be nats. Here it will be nats. And finally the unit will be nats. So what we got the final equation, that is 1 Hartley is equal to 2.3 nats. This is the relationship in between hats and nats, Hartleys and nats. And similarly, you also can establish what is 1 nats is equal to how much Hartley. That is equal to 1 divided by 2.3. So if you want to find what is the value of 1 nats in terms of Hartley, it will be 1 divided by 2.3. So 1 divided by 2.3 will be 0.43. This much Hartleys. You can use the calculator and tell me the answer if I'm wrong. Okay. So now looking at this relationship that 1 Hartley is this much nats. So similarly, we can also establish a relationship in between Hartleys and bits. So what we have to do, we have to begin with this particular equation where we have written 1 Hartley is equal to I divided by log base 10 1 by P. Here we replace the term I by this particular equation having the unit nats. So if you want to establish a relationship in between Hartley and bits, so you follow this equation. So you write this equation here. So what you will write, only in place of E, it will be 2. So wherever E is there, you just rewrite that 2. So here also E, it will be 2. This E will become 2. This E will become 2. This E will become 2. So finally, you will get log base 2 10. So what you will get here, 1 Hartley is equal to log base 2 10. So what is log base 2 10? That is equal to 3.32 this much bits. So these values I have already calculated. The values are with me, so that's why I'm writing directly. You can use the calculator and you can verify whether you are getting this value or not. So this is the relationship in between Hartleys and bits. Similarly, using this equation, it is also very easy to establish a relationship in between bits and Hartleys. So what is the value of 1 bits in terms of Hartley? It will be 1 divided by 3.32. So that result will be 0.3 approximately Hartleys. All right. So by this way, we have established relationship Hartleys and Nats, Nats and Hartleys, Hartleys and Bits, Bits and Hartleys, but we have not made any relationship in between Bits and Nats. That relationship we have not established. But using this equation, you can do it. How you can do it? See, 1 Hartley is equal to 2.3 Nats. So we are going to establish a relationship in between Nats and Bits. Okay, so we have to replace this Hartley in terms of bit. So 1 Hartley is equal to how much bits? That we have to find out. Here it is. 1 Hartley is equal to 3.32 bits. So you just write here 3.32 bits. So that means 3.32 bits is equal to 2.3 nats. And from this we can find out 1 bit is equal to 2.3 divided by 3.32, this many nats. So what is the result? 1 bit is equal to 0.693 is the result. This many nats. All right. And once you find out this relationship, from this you can also find out what is 1 nats. That is equal to 1 divided by 0.693. So 1 nats is equal to how much bits? It will be 1.443, this much of bits. So see why we are going to study this relationship. The reason being is that suppose we have calculated the information. Suppose we have calculated the information, or we have calculated the entropy. Suppose my entropy is something called as x bits per symbol. I have got the value of entropy is x bits per symbol. And it has been asked that what is the value of entropy in terms of nats per symbol. It has been asked to find out the entropy in nats per symbol. So if we know that 1 bit is equal to 1.443 bits, so we can write as x into 1.443, this many. This will be the answer of entropy in the unit of nats per symbol. Or if it is very difficult to remember this relationship, because you have to remember at least 3 equations. Why? Because if you remember this equation, 1 Hartley is equal to 2.3 nats, then this equation can be obtained using this equation. So at least you have to remember 3 equations. So if remembering of this equation is also difficult for you, then the other way, what you have to do, if you have to find the entropy, then you have to change the base of the logarithm, and you have to recalculate the entropy. If you don't remember this thing, then you find out the entropy, or you find out the information using the original expression. Suppose if you want to calculate in units of nats, then use the log base E1 divided by P and recalculate the value once again. All right, so this is what I was trying to explain. Now, let me take an example for you. This is the example given. Find the entropy of a source in nats per symbol of a source that emits the 1 out of 4 symbols with probabilities 1/2, 1/4, 1/8, 1/8. What to find out? We have to find out the entropy of a source. How many symbols the source is emitting? It is emitting 4 symbols. What is the probability of those symbols? 1/2, 1/4, 1/8, and 1/8. So what is given? P1 is equal to 1/2. First probability. Probability of second symbol is 1/4. Probability of third symbol is 1/8. And probability of fourth symbol, that is also 1/8. But you have to calculate the entropy in the unit of nats per symbol. So there are two different ways or approaches you can find out this. So one is using this. You can also calculate I is equal to 1 to 4 because there are 4 different symbols. So P I into log base E 1 divided by Pi. So in place of log base 2, you have to use log base E because it is asked the unit should be nats per symbol. So you can use this equation. This is one approach of calculating the entropy as a unit of nats per symbol. Or the other way, what you can do, you can use this equation I is equal to 1 to 4 Pi log base 2 1 divided by Pi. But the unit of this entropy will be bits per symbol. It is not nats per symbol. So whatever the value you will get, so you will get in terms of bits per symbol. Okay, so I will let me write because I have calculated the value I have got, that is 1.75. So 1.75 bits per symbol by using this equation. Okay, but we have to calculate as a unit of nats per symbol. So once we can know that 1 bits per symbol is how much nats per symbol, or not exactly that 1 bit is equal to how much nats. You can follow this. 1 bit is equal to 0.693 nats. Okay, so this many bits will be how much nats. So you have to multiply. This equals 1.75 into 0.693. Whatever the result, the unit will be nats per symbol. So two way, either you directly use this equation, logarithmic of base E, or the other way you can use the logarithmic of base 2, and you multiply the conversion formula. So that's all about the relationship in between different units of information or different units of entropy or average information. Next, what we are going to see that let us analyze the entropy and let us study the characteristics of entropy. In order to do that, let us take an example. From that example, we will do a plot. And once we can make a plot from the example, then we have to list some of the properties of entropy. So the example is, it is given this is the example. A binary source is emitting an independent sequence of zeros and ones with probabilities p and 1 minus p respectively. So that means the binary source is emitting two different symbols, 0 and 1. So 0 is transmitted at a probability of p, 1 is transmitted at a probability 1 minus p. In the last line, plot the entropy of source versus p. P is the probability. So what we have to plot? We have to plot this entropy versus probability and comment on the result. So in the comment, we have to comment some properties of entropy. So let us list the expression of entropy. So what is it? Expression of entropy, that is equal to summation I is equal to 1 to 2, because here we have two different symbols only. So pi log base 2 1 divided by pi, or that equals p1 log base 2 1 divided by p1 plus p2 log base 2 1 divided by p2. What is p1? It is the probability for bit 0. P2 is the probability of bit 1. So it is given the probability of bit 0 is p. So p1 can be replaced with the value p log base 2 1 divided by p, plus p2 is having value 1 minus p log base 2 1 divided by 1 minus p. So this is the expression of entropy when the source is transmitting two symbols, 0 and 1. So whenever you have to make a plot and the plot is in between the entropy and the probability p, so our vertical axis will be the entropy axis and the horizontal axis will be the probability axis. And you people are aware that the probability is having the minimum value 0, maximum value 1. So probability always ranges in between two values, that those are 0 and 1. So in this example, what we are going to do, we are going to take, or we are going to vary the value of p in between 0 and 1, and those values are 0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, so on like that up to 1. We'll take different values of p, and we are going to calculate the corresponding value of h of s for different values of p, and after that we will make a plot of entropy with respect to p. That is what we are going to do now. Okay, so when probability is equal to 0, so what is the value of entropy excess? So we have to follow this equation. So that equals, probability is equal to 0. So 0 into log base 2 1 divided by 0 plus 1 minus 0 will be 1 into log base 2 1 by 1. So 0 multiplied with anything, it will be 0. Then log base 2 1 divided by 1. So log base 1 is 0. So this is 0. So when probability is 0, entropy is 0. So what does that statement indicates? When the message has 0 probability of occurrence. 0 probability of occurrence means the message itself is not there. Okay, that means it has no average information. That is obviously true. If the message has no occurrence, if the message is not occurring, then it has no information. Next, we'll take p is equal to 0.1 and calculate the entropy. So p is 0.1, it will be 0.1 log base 2, 1 divided by 0.1 plus 1 minus p will be 1 minus 0.1, it will be 0.9 log base 2, 1 divided by 1 minus p. So p is 0.1, 1 minus 0.1 will be 0.9. So this value is 0.469 bits per symbol. Now at probability 0.2, we similarly can write this will be 0.8 because 1 minus p and its value will become 0.722 bits per symbol. Further probability when it is 0.3, HS is 0.3 log base 2 1 by 0.3 plus 1 minus p, it will be 0.7. This answer is 0.881. Next probability is 0.4. And the average information is 0.4 log base 2 1 by 0.4 plus 1 minus p will be 0.6 and the result will be 0.971. And this point is very important point. Just have a note of this calculation. When probability is 0.5, so it will be 0.5 log base 2 1 by 0.5 plus 1 minus 0.5 will again be 0.5 log base 2 1 divided by 0.5. So what it will be, see, 0.5 is how much? 1 divided by 2. So 1 whole divided by 1 by 2, it will be 2. So log base 2, it will be 1. 1 multiplied with 0.5 will be 0.5. Same thing, here also it will be 0.5. So 0.5 plus 0.5, it will become 1. So 1 bit per symbol. That's a very important point to note. Now just have a note of this. P is equal to 0.6 and we are calculating the entropy. So probability is 0.6 log base 2 1 divided by 0.6 plus 1 minus P. So 1 minus 0.6 will be 0.4 log base 2 1 divided by 0.4. Okay, I am not writing the value. I will write it later. Now probability is 0.7. It will be 0.7 log base 2 1 by 0.7 plus 1 minus P will be 0.3, then log base 2 1 divided by 0.3. Okay. Now let us come to the answer. When probability is 0.6 and when the probability is 0.4, see in probability 0.4 you have a term 0.4 into log base 2 1 by 0.4. Here also it is 0.4 log base 2 1 by 0.4. Here 0.6 log base 2 1 by 0.6. Here log base 2 is 0.6 into log base 2 1 by 0.6. So same thing is both two equations are correct. So answer will be same. 0.971 bits per symbol. That means whatever is the information at probability 0.4, the same is the information at probability 0.6. Similarly, you can make a note of this probability at 0.7. So whatever this value, the same value is also here. And this value is also here. So what the value it will be 0.881. This is bits per symbol. Okay. So similarly, we can calculate, I have calculated for probability 0.8, for probability 0.9, I have calculated the average information or entropy that is equal to for 0.8, how much it will be? It will be same as 0.2, that is 0.722. 0.722 bits per symbol. Similarly, when probability is 0.9, it will be same as 0.1. This one, 0.469. Correct? Now let us calculate that probability 1. Final value is 1. So that I will write. That is equal to P into log base to 1 by P. So P is 1 into log base to 1 by P plus 1 minus P is 0 into log base to 1 by 0. This is, if you see, this is same as also probability of 0. Okay, the same thing is come 0 into log base to 1 by 0 plus 1 into log base to 1 by 1. So 0 into log base to 1 by 0, 1 into log base to 1 by 1. So it will be also 0. Now, if you go for plot of entropy as a function of probability, so the probability ranges between two values 0 and 1, and your entropy will range in between. See, we have calculated the values. The minimum value of entropy is 0. The maximum value of entropy is 1. So entropy has a minimum value 0 to maximum value 1. So when the probability is 0, entropy is equal to 0. When probability is 0.1, entropy is 0.469. When probability is 0.9, entropy is 0.469. So at 0.1 and at 0.9, both probabilities, entropies are same. At probability 0.2 and at probability 0.8, your entropies are same. At probability 0.3 and at probability 0.7, the entropies are same. At probability 0.4 and at probability 0.6, the entropies are same. And at probability 0.5, the entropy is 1. You can see at probability 0.5, the entropy is 1. Okay, so if you join all those values, you will have a plot like this. A continuous plot we will get once you join the points like this. So this is the plot of entropy versus the probability of occurrence. So what are the characteristics? So let us analyze the plot and list out some of the characteristics of entropy. So we will list out some characteristics of entropy. So first characteristics is the entropy is a continuous plot as a function of probability. When the probability varies between two values 0 and 1. So first property is it is a continuous plot. Second property of entropy is the entropy is symmetric. See, this point is 0.5. So your entropy is symmetric across what? Across the equiprobable point. So I have, you see, if you look at this particular line, whatever portions are there in the left side, the same is there in the right side. So it is symmetric across this 0.5. This 0.5 is called the equiprobable point. Why it is called equiprobable point? Because if p is equal to 0.5, then 1 minus p, that will also become 0.5. So p is what? It is the probability that we are transmitting bit 0. 1 minus p is what? It is the probability we are transmitting bit 1. So both the symbols 0 and 1, they are transmitting at equiprobable. They are transmitted at equal probabilities. So 0.5 is called the equiprobable point, and the plot is symmetric along the equiprobable point. Third characteristics of entropy is the maximum value of entropy is equal to log base 2, where log base 2 q, where q is number of symbols. In this particular example, what is the value of q? In this particular example, the value of q is equal to 2, because we have only two symbols. One symbol is 0, another symbol is 1. So we have only two symbols. So the value of q is equal to 2. So in this particular example, q value is equal to 2. So what is log base 2 of 2? This is equal to 1. So maximum value of entropy we are getting, that is equal to 1 for this particular example. You see here the maximum entropy we are getting 1. In this calculation also you see maximum entropy we are getting 1. That is at equiprobable point. Okay. So this is one characteristics. Now, fourth characteristics of entropy. Fourth characteristics of entropy is, suppose we have two independent symbols. One is having entropy h of s, another is having entropy h of s dash, then the total entropy, that is h of s double dash, can be written as h of s plus h of s dash. So this property of entropy is called additive property. Okay. Now fifth property, that is called the source efficiency. Which is denoted by the symbol that is eta of s. So what is eta of s? Eta of s is the average information or entropy divided by the maximum information or entropy. This is called the source efficiency. So what is the value of HS max? What is the value? It is nothing but log base 2 q, as per which property? Property number 3. The maximum value of entropy is log base 2 q. And what is q? So q is the number of symbols. Okay. And it happens when all the symbols are of equal probability. This maximum value is always attained where you are attaining the maximum value of entropy. Where you are attaining? We are attaining at 0.5. So that is the equal probability point, equiprobable point. Okay. So that maximum value and the ratio, this is in the numerator, it is the average information. So this is called source efficiency. And the final property of entropy, that is called source redundancy. So what is source redundancy? It is denoted by R subscript eta s. We know eta s represents the source efficiency, but R subscript eta s represents the source redundancy. That is equal to 1 minus efficiency or source efficiency. Okay. So this is different characteristics we have observed by looking at the entropy versus probability plot of a source which is emitting some number of symbols at some different probabilities. In the next class, when we will meet again, we will take an example and we will try to verify all those properties of entropy based on the things or the properties which we have noted down. So thank you for the class. If you have any question, you can ask.